Section 1.5 Nested Quantifiers. Let p of x, y be a propositional function in two variables, x plus y equals 0, with x and y having domain the set of all real numbers, R. The statement for every x there is a y, such that p of xy means for every x there exists a y, such that x plus y equals 0. This is a true proposition. It is helpful to think in terms of nested loops. We loop through x, and for every x we loop through the values of y until we find a y for which x plus y is true. It happens when y is selected to be negative x. Since this can be done for every x, the proposition for every x there is a y such that x plus y is equal to 0 is true. The statement there is an x and there is a y such that p of xy means there exists an x and there exists a y such that x plus y equals 0. This proposition is true. The statement there is an x such that for every y, p of xy means there exists an x such that for every y, x plus y equals 0. This proposition is false. We look through x and we look for x, at least one x, such that when we loop to y, x plus y is always true. No such x can be found because once x is selected in some way, y cannot vary because if we want x plus y to be 0, y must be selected to be equal to negative x. For any other selection of y, x plus y will not be 0. The next statement, for every x and for every y, p of xy means for every x and for every y, we have x plus y equals 0. Again, this is false. We can figure this out with looping. The order of quantifiers for every x and for every y, p of xy, and for every y and for every x, p of xy have the same meaning. So here the order of x and y doesn't matter because the quantifiers are the same. The same way, if we have two existential quantifiers, the order of the variables doesn't matter. If the quantifiers are different, existential applied to x, universal applied to y, then the order matters because, as we know, this proposition is false there exists an x such that for every y, x plus y is 0, it is false. But if we replace the order, switch the order, so if we write first for every y, then there exists an x such that x plus y equals 0, this proposition becomes true. So if we switch this to this, from false, the proposition becomes true. So the order in that, the order of the variables when the quantifiers are different matters. The De Morgan's laws for quantifiers can be used to negate propositions containing nested quantifiers. So let's consider again this propositional function x plus y equals 0. What is the negation of for every x there is some y such that p of xy? We know from the De Morgan law for quantifiers that we can move the negation over universal quantifier like this, but we have to replace this for every x with there exists an x. Again, here the negation can be moved over the existential quantifier, but we have to replace there exists a y with for every y. And then we stop in front of p. The last statement, this one, means there exists an x such that for every y, x plus y is different from 0. The negation of x plus y equals 0 is x plus y different from 0. Is this a true proposition? We started with a true proposition. So its negation will be false. There exists an x such that for every y, x plus y is different from 0. This is false. In the next example, we consider this statement. For every real number epsilon greater than 0, there exists a real number delta greater than 0, such that whenever the absolute value of x minus 3 is between 0 and delta, then the absolute value of x squared minus 9 is less than epsilon. This is the formal definition of the limit. The limit of x squared when x approaches 3 is 9. In calculus, you'll see that this is true. When x approaches 3, x squared approaches 9. The formal definition looks very complicated. In calculus 1, you consider less complicated ways of establishing this. but the formal definition can be written symbolically this way. So this definition symbolically can be written: for every epsilon there exists a delta such that for every x, if the absolute value of x minus 3 is between 0 and delta, then the absolute value of x squared minus 9 is less than epsilon. And in this definition, epsilon and delta have domain the set of all positive real numbers. If we set the domain of x, epsilon and delta to be the set of all real numbers, then we have to apply here these inequalities. So the same definition can be written this way if we allow epsilon and delta to have domain the set of all real numbers. For every epsilon greater than 0, there exists a delta greater than 0, such that for every x, if the absolute value of x minus 3 is between 0 and delta, then the absolute value of x squared minus 9 is less than epsilon.